Let's continue our discussion about exponential mathematical models. This is part 2 of exponential models. So we had carried out the one-dimensional flow analysis for the differential equation dx dt equals b times x, where b is a constant, real number, and there are two scenarios, b being positive, b being negative, and for each of those scenarios we were able to come up with this horizontal line where the state variable appears on the horizontal line. There are arrows. The other thing we have on this horizontal line for each case are the values that we call the equilibrium points. When b is positive, the equilibrium point 0 is an equilibrium point where the flow in x, the solutions x, are moving away from 0. And we would say that 0 is unstable, is an unstable equilibrium point. But when b is negative, we come up with a one-dimensional flow analysis in which the arrows are pointing towards that equilibrium point, which is 0, and we call that stability. So what we would like to do next is that we can sketch what is the behavior of the solutions by taking the information that we have here as a horizontal. What we'd like to do in each scenario is basically take this horizontal line and place that vertically, as if it were a vertical axis of this new plot. And in this new plot, we're going to have on the vertical axis x, this would be x of t. Remember, t is the independent variable, and t will be on the horizontal axis. So when we bring this information, this point is 0. So that means that point is going to be located here, and then we can draw those arrows. So taking that line with arrows and placing that on the vertical axis would give us this type of picture. Remember, here we have x, this is what I'm calling here, x bar equals 0. That's precisely what we see that as a filled-in dot. And so what we'd like to do next is to sketch the solutions x of t. So that idea that x converges to 0 is something that we can depict here. We start, I'm starting my drawing right there. This assumes this would be one potential x of 0. If that initial condition is started certainly at a value that is above 0, then the time solution will be a time solution that kind of looks like this. Okay, if we start a little farther closer to 0, then this would be another curve, another x of t, and with another initial condition that's actually closer to 0, then the time solution would look like this. If we were for some reason interested in starting with initial conditions that are negative, then those solutions will approach the value of 0 in this way. You would get a little closer to 0 from below, then the time solution would look like that. So this is a picture basically illustrating the fact that the limit of x of t when t goes to infinity is equal to the stable equilibrium point. Remember, this is what we had established before, that x equals 0 in this case would be stable, and that limit is exactly equal to 0. So that's the implication of having a value in this differential equation, that constant multiple, this b constant, having that negative implies that this exponential function has a negative number in its argument here, b times the independent variable t, and that means that this whole thing as a function of t is an exponentially decaying function, and it decays exponentially to 0. Now, what we have on the other scenario is the following. We have a one-dimensional flow in which the arrows are pointing away from 0. So we're now going to draw this horizontal axis as a vertical axis. So in this case, this is precisely the location of x bar equals 0, right? That's exactly what's here at the origin. X of t is still the vertical axis, t is the horizontal axis. On the vertical axis, the arrows are pointing away from that equilibrium point, and that would mean that if we start solutions of x of t, let's say one initial condition right here, then as a time function, that would look like this. If we started a little farther up, that as a time function looks like this. If we started a little closer to 0, then that function would look like that. And if we started below 0 at negative values, then we'd have some cases of things that are going to negative infinity rather quickly, right? So this is the pictorial representation depicting the case in which here, well, 0 is this equilibrium point is considered unstable. That's what we had established with the one-dimensional flow analysis. But on the language specifically of the curves that are above the 0 and the vertical axis, this is what we would consider exponential. These curves right here, every single one of them, okay, every single one of these curves, this is what we would consider exponential. This is what is considered exponential growth. Okay, so things, whenever the initial conditions are positive and B is positive, then those solutions, so let's look at the shape of those solutions, these things with a positive initial condition and a positive value of B, as a function of time, this whole thing is something that is exponentially growing. And so basically that's the other name that these two scenarios have. When B is positive, we have exponential growth, and when B is negative, we have exponential decay. So in reference to exponential decay, there is a terminology formally phrased as radioactive decay. And one way is basically the same type of differential equation. One way of writing down this differential equation for radioactive decay is explicitly writing that constant. Suppose you have a positive constant here called positive k, and so we write negative of that positive number, so making sure that this parameter here, with this assumption, negative k would be a negative number, right? So we could write something like minus k times q. So let's say q denotes quantity, mass, volume, weight, q as a function of t. And so we can write this differential equation basically saying that the rate of change of that mass of the amount of material is equal to minus k times q. There is an initial condition q sub 0. Using separation of variables, we can find the solution of this linear differential equation, and that solution, assuming that is starting at t sub 0, the solution has this particular form. So in this context, when we're describing things that are functions of time but they decay exponentially, it is also pertinent to look at the calculation of the so-called half-life, right? So assuming that q is an exponential function of t, and assuming that we have an initial condition, initial amount of material q sub 0, the so-called half-life is the time that is required for the material to become half of what it was, right? So is the time, say, tau units after the initial time t sub 0. So the amount of material at time t sub 0 plus tau is the initial condition divided by 2. So once we have an expression for q of t, evaluating that expression at this particular time, t sub 0 plus tau, leads to an expression in which we can equate q0 e to the minus k tau. We can equate that to that quantity q sub 0 divided by 2. And then we can solve for tau. And if we solve for tau, then we would find this so-called half-life. And so in this case, these calculations are not too difficult. Tau here will be equal to natural log of 2 divided by that constant k, right? So remember that constant k comes from how we were writing q prime equals minus k times q.